Hello students, once again I invite you to another lecture of engineering physics. Myself Dr. Shweta Prakash, and the topic which I will be discussing with you today is the electromagnetic field theory. This is our module 2 from the engineering physics course, which is studied in BTech first year. All right. So as I had done in the previous discussion, first I will give you the idea of the topics which are discussed in this unit 2, and then I will come to the particular topic which I will be discussing with you today. So these are the topics. As you can see, we are having continuity equation for current density. Then we are having displacement current, modifying equation for the curl of magnetic field to satisfy continuity equation, Maxwell's equation in vacuum and in non-conducting medium, energy in electromagnetic field, Poynting vector and Poynting theorem. These are the topics for the unit 2, all right. And then this topic which you are able to see, plane electromagnetic wave in vacuum and their transverse nature, this topic I will be discussing with you. All right, some other topics which are here, they are relation between electric and magnetic field of an electromagnetic wave, energy and momentum carried by electromagnetic waves, resultant pressure and skin depth. So this was the discussion of all the topics which are there in the unit 2. Out of these topics, I will be concentrating on this plane electromagnetic wave in vacuum. So what I will do, I will first discuss an introductory part which will have the discussion for the electromagnetic waves, and then we will come to our particular topic. So let us begin. So as you can see, the topic is plane electromagnetic waves in vacuum and their transverse nature. All right. So what are the electromagnetic waves? Basically, they are generated when electric or magnetic field becomes time varying. All right. If the electric field or the magnetic field is having a time dependence also, so then we can say that we can expect that the electromagnetic waves will be generated. All right. They are usually emitted by a moving charged particle. This is one idea about the electromagnetic waves. Now they consist of electric fields and the magnetic fields which are vibrating perpendicular to the direction of propagation of the wave. So in this way, we can understand that the electromagnetic waves, they are transverse in nature by this property. All right. In the later discussion, we will also see that how they are showing their transverse nature. All right. So what happened now after we are having the idea of the electromagnetic waves? Now we will go to their study. So if we talk about their study, so their study was done by J.C. Maxwell in 1865, where he developed 4 mathematical relations between the electric and the magnetic fields, and these 4 relations are famously known as the Maxwell's equation. All right. So these equations he used to study the nature of the electromagnetic waves. These are very famous equations, and these are the only equations which are used in the study of electromagnetic theory. All right. Now this is the electromagnetic radiation spectrum. As I have told you that initially we will be having a discussion of the electromagnetic waves. All right. So with this spectrum, you can see that there are different regions in terms of wavelength, and these regions are showing that what wavelength is having which type of radiation. Like this region is showing that the gamma rays are present here. All right. This region is showing that the X-ray is present here. The ultraviolet region you can see, the visible region, all right, and so on. So this is how, with the help of this spectrum, we can see that how the the radiation changes for different wavelength region. All right. In the same way, we can see here also. All right. So I suppose now, up till now, we are somewhat familiar with the electromagnetic waves. All right. What are the electromagnetic waves and what are their nature? All right. So this again, this description here can show you, give you a picture of the electromagnetic waves. Like if we represent the electromagnetic waves with the help of the Cartesian coordinate system x, y, z, so we can show it in this manner, like this part. All right, this direction, this x axis, suppose it is showing the direction of propagation where the wave is moving. All right, if we look at this part, so we can consider that this is the electric field in this direction. So this part is showing the vibration of the electric field. All right, the behavior of the electric field. So this way we can see the electric field. All right, and then we come to the magnetic field. So suppose this is the y part, this is the x part, so this can be the z part, if we are talking about the Cartesian coordinate system. All right. So here what happens, this is the z part, and here the magnetic field can be represented by this z axis. All right. So we can see the magnetic field represented by this blue part. And if you look at this part, these parts, then you can see that the electric field is moving in a manner that it is perpendicular to this blue part, that is the magnetic field part. So this is showing that in the electromagnetic wave, the electric field and the magnetic field, they are mutually perpendicular to each other. And then what happens? We are familiar with this x, y, z coordinate system. So we know that x, y are mutually perpendicular, x, z are perpendicular, y, z are mutually perpendicular. All right. So when this x axis is showing the direction of the propagation, so it means that these y and z will be perpendicular to this x axis. So that means the electric field and the magnetic field, they will be perpendicular to the direction of propagation. And this means that the electromagnetic wave will be showing the transverse nature. All right. So if we represent the electromagnetic wave with the help of the Cartesian system, then this can be the form by which we can represent to understand the behavior. Further, again, we will be able to see with the help of the Maxwell's equation how the transverse nature can be detected. Then now we come to our topic, which is the propagation of electromagnetic waves in free space or vacuum. So first, since we have already had a discussion about the electromagnetic waves, we can now have a discussion of the free space. We can understand what is the meaning of the free space. Now, free space or vacuum is generally, it is meant that there is nothing present there. In terms of charges, we can say that no charges are present there. All right. So that is the medium which is known as the free space or vacuum. So when we are having this free space or vacuum discussed here, so then it means that there is nothing present here. So then how do we define that kind of medium? How do we assign certain properties to such a medium so that we can study? So what do? We can just assign simple properties, like we can assign electrical permittivity epsilon naught for such medium. We can assign magnetic permeability mu naught for such medium. So epsilon naught for the vacuum is having this standard value. All of you must have used this value in numericals. All of you are familiar with this numerical value of epsilon naught. All right. Similarly, the magnetic permeability, which defines the free space, is mu naught, and again it is 4 pi is equal multiplied by 10 to the power of -7. All right, and again all of you are familiar with this value. All right, we have done a lot of numericals in our previous classes. I mean, you have done with a lot of numericals in your previous classes based on the electric field and the magnetic field and the electrostatic forces and so on, where you must have used these parameters. So the values are not new to you all. All right. So now this is how we can define the free space. All right. And what happens in this discussion, in this topic, we are having some new values or parameters for the free space, namely the charge density rho, charge per unit volume, you can also say. Charge density rho equals to 0. All right. And then the other proper parameter is the conduction current density J. All right, that is current per unit area is equals to 0. So these will define the free space or the vacuum completely. All right, how do we define? By these two parameters and by this charge density and the conduction current density J. All right. Next, what happens? Next, we define another property, displacement current density D. And how is D defined? D is equal to epsilon naught and E. E is the electric field and epsilon naught we already know. It is the permittivity in the free space. And similarly, we define another value or relation, rather we can say, this is the magnetic flux density B is equals to mu naught H. Mu naught, again I would like to remind you, it is the permeability in the free space, and H, it is the electric field. All right. So whenever we have to discuss the propagation of the electromagnetic waves in a particular medium, so we have to define the medium first. We have to understand what are the parameters which we are going to use to study the propagation. So that is why I had defined these parameters, and then now we will be discussing the propagation. All right. So now this for the discussion of the propagation, we will be using the Maxwell's equation, as we have already discussed in our first slide, that it was Maxwell who studied, who designed certain equations which can be used to study the these electromagnetic waves. All right. So these are the 4 equations which we were talking about. This is the first equation, which is the divergence of E is equal to 0. And then the second equation, Maxwell's second equation, curl of E is equals to minus del B by del T. And again, divergence of B is equals to 0. This is the Maxwell's third equation. And this is last equation, that is the fourth equation, is curl of B is equals to mu naught epsilon naught del E by del T. All right. One interesting part about these equations is that they are also, apart from Maxwell's first, second, third, fourth, these names, they are also having another name. Like this first equation is the Gauss's law of electrostatics. All right. The second equation, this is basically the second equation. This is the Gauss law of magnetostatics. And this is the third equation. This is the third equation actually. So this third equation is the Faraday's law of electromagnetic induction. And then the fourth equation is the modified Ampere's law. So these are the names for these equations. By these names, the equations are also known. All right. So now we will be, so this is the Maxwell's equation. All right. And in free space, it is written like this. All right. This is the free space equation. General equation is having some other form. All right. So what do we do to study the propagation of electromagnetic waves? We perform certain calculations with these equations. All right. So what do? We first find out the electromagnetic wave equation for this electric field particularly. All right, and then we will find out for magnetic field, and then we will combine, and then we will have the final electromagnetic wave equation. All right. So what do? We start our study with the electric field, and what happens for the study of the electric field? We have started our discussion with the Maxwell's third equation. All right, I hope all of you remember the third equation. This is the third equation. Curl of E is equals to minus del V by del T. So we have chosen this equation as the starting point. Now what do? We take curl of this equation. All right. So curl of this equation is like this. This operator del cross of a vector is known as curl. All right. It means this is written here. We can write curl of E is equal to minus del V by del T. This equation can be written like this also. So that is the meaning of curl. All right. So curl of E is like this. Now the next step, we take curl of this equation. So it becomes curl of E now. All right, is equals to minus curl of del B by del T. So this is the equation which we are now getting. Next, what we do? We now solve this vector identity. This curl of a vector. This curl of E is a vector identity, and it is solved as this is gradient divergence E minus del square E. So this is the vector identity which is used here. All right. So we use this vector identity for our calculation in this equation. When we do this, so in place of curl of E, we are having gradient divergence E minus del squared E. And on the right hand side, we are having minus del by del T of curl of B. You see this, we have interchanged this curl and del operator now. Earlier we were having this, now we have interchanged, and so we are having del by del T of curl B. All right. So up till here we have done our calculation. Now let us see what do we get in the next step. Now what happens in the next step? Here. Now what happens in the next step? We have to concentrate here on divergence of E. All right. So divergence of E, if we concentrate here, we have divergence of E equal to 0 by the Maxwell's first equation. All right. So divergence of E is equals to 0 by the Maxwell's first equation. All right. We have seen when we were writing the Maxwell's equation for the free space, we have seen the first equation is divergence of E equal to 0. So we will use this part in our calculation. And also when we look at the Maxwell's fourth equation, we have found that the fourth equation is curl of B is equals to mu naught epsilon naught del E by del T. We have found this. All right. So these two parts we will use, and we will see what happens to our this equation. Here we will use these two parts here, like this will become to 0. All right, by Maxwell's first equation, and this part is going for the fourth equation. For the fourth equation, we are having this part. All right. So now what happens? Now when we use these things, we are getting minus del squared E and is equals to minus del B by del T mu naught epsilon naught del E by del T. All right. So minus and minus cancels off, and we are left with this del squared E equals to mu naught epsilon naught del squared E by del T squared. All right. So this is the wave equation for the electric field in the electromagnetic wave equation, waves. All right. So this is for only electric field, which is obvious. You can see we are only having E here, electric field is only present. We are not having any term of the magnetic field. So, this will represent the wave equation which the electric field will follow in the electromagnetic waves. That is what this expression is showing. All right. And I would like to explain you about the del squared part here. All right. There is nothing confusing about this del squared, because this del squared is an operator and it means like this. This operator is having this value. All right. So, there is nothing confusion about this part. So, this is the operator del squared. All right. And this you already know, del squared by del t squared. It is a time derivative. Similarly, this del square is having the position derivative like this. All right. So, this is also clear now. And once we have obtained the wave equation for the electric field, we can obtain the wave equation for the magnetic field using the same steps, same procedure. All right, like we can earlier we had for the electric field, we had started with the Maxwell's third equation. For the magnetic field, we can start with the fourth equation. What is the fourth equation? Fourth equation is this one. This one, we can start with this. This can be our starting point. And what will we do? We will take curl of this, just like we have done for the electric field. All right, we have taken curl in the next step, and then we have used the identity, and then we have used the Maxwell's equation and obtained this part. So, the same steps we can do for the magnetic field, and when we will do these same steps, we will obtain this equation for the magnetic field, which will be del squared B is equals to mu naught epsilon naught del squared B by del T squared. So, you can see the same equation, same form of equation is obtained, which we have obtained for the electric field. But this is the equation for the magnetic field. So, if we want to see that what is the behavior of the magnetic field in the electromagnetic waves, we will go to this equation. If we want to see what is the behavior of the electric field in the electromagnetic wave, we will go to this equation. All right. So, if we want to see the behavior of the electromagnetic wave, what we have to do? We have to combine these equations. So, when we want to talk about the wave equation for the electromagnetic wave in the free space, so we have to mention both these equations. All right. So, we have to mention both these equations, and together they will give us the wave equation for the electromagnetic waves in the free space. That is, this del squared E is equals to mu naught epsilon naught del squared E by del T squared. Del squared B is equals to this part. All right. So, this is our electromagnetic wave equation in the free space. This is well known in this form. All right. So, in this way, you can see by using the Maxwell's equation, it is very easy to study the behavior of the electromagnetic waves in the free space. And to study the behavior, we will first have to obtain their wave equation. So, that we have done now. We have obtained the wave equation, and now we will study other properties of these waves in the free space. So, one property of these waves is the transverse nature. Although we have theoretically discussed, all right, that the waves are transverse in nature, we have shown that the waves are transverse in nature because the electric field is perpendicular to the propagation vector, the magnetic field is perpendicular to the propagation vector. We have shown with the help of that diagram. You must have seen this in the diagram. All right, this with the help of this, if we represent the electromagnetic waves with the help of this Cartesian coordinate system, then we can show it in this manner. But this is not sufficient. This type of thing is not sufficient to prove that these waves are having transverse nature. All right. And also now we know about the Maxwell's equation, so we can obtain this transverse nature by using the Maxwell's equation. All right. So that is the same thing which we are going to do here. For that, again, as you have seen that we are selecting one of the field. Either we are first studying for the magnetic field and then we are studying for the electric field, either we are studying the other way, because you can see that both the fields are having the same behavior. They are having the same nature, the same behavior. They are both are having the vibrations which are perpendicular. All right. So in this way, if we study for one of the field, so we can say that similarly the behavior will be for the other field. So that is why we select one field first. So here again we have selected the electric field first. All right. And what do? We have selected one direction. Let us say that the electric field is in the x direction. So the electric field can be written as Ex, which is showing the direction x, is equal to E naught e to the power I k dot x minus omega t. So this is the way which we can represent the electric field. And electric field is having other components also, Ey and Ez, let us say, and they can be represented in the same manner. All right. That is why we can use this term similarly here. All right. Now what happens? Now we start with the Maxwell's first equation, which is what? Which is divergence of E equals to 0. So we start with the Maxwell's first equation, and divergence operator we are using here. So divergence means del by del x of I plus del by del y of j and plus del by del z of k. This is the divergence operator. All right. Here we are having the electric field with all the three components Ex, Ey and Ez. So this divergence operator is going to be applied on this electric field. All right, component wise. So what happens when it is applied? When it is applied, we will have del Ex by del x plus del Ey by del y plus del Ez by del z equals to 0. All right. So this is how the divergence E is obtained. All right. So now we work out this part, del Ex by del x. This we solve this part. All right. And then similarly, we will be having the solution of del Ey by del y, del Ez by del z. So this is our next part. Now, when we solve this del Ex by del x, all right, let us see what happens. So del Ex by del x, this is del by del x, and then we will write down the component of the form of this Ex, which was this. Ex is this. So we will write down Ex here now. All right. So E naught and then e to the power, and then this is kx minus omega t. So this is now written like this. Now we will differentiate. All right. So what will happen? We are going to get what? E naught will be as it is, because it cannot be, this cannot be applied. Del by del x cannot be applied on E naught. All right. So del by del x will be applied here. All right. So we are having this I, we are having this k. All right. We can have this kx part. X is representing the x component. So that is why we can write here x. And then we will have what? We will have e to the power I, and we will have kx minus omega t, this part. Okay, all right. We can have this differentiation like this. Now what happens? E naught and then this will be what? Ex only. We can have I, kx, and this whole part is Ex. So we will write this part here. All right. So when we differentiate del Ex by del x, we will have this part. All right. This is how this term is obtained. Similarly, when we obtain del Ey by del y, we will have this ky Ey, and we will obtain del Ez by del z. So we will have this kz Ez. And in all these three terms, we will take I common. So we will have kx ex plus ky ey plus kz ez. All right. And then if we look at this term properly, this whole expression properly, so we can say that if we take the dot product of k and e, then we will obtain these terms. All right. Let me show you how we will obtain. Suppose k, what is k now? This vector k is the propagation vector k, all right. So if we write this in terms of components, so how it can be written? Kx I, all right, plus ky j plus kz k. All right. Similarly, what is E? We have already seen vector E is EXI plus EYJ plus EZK. All right. So now you can, now it is visible. Now if we take the dot product, so it is like this KXEX, KYEY, KZEZ. So it is clear now. So this dot product K dot E will be giving us this part, this expression. So in place of this whole expression, we can write down K dot E. All right. So that is what we have done here, K dot E. Now what happens? Now we are having I K dot E equals to 0. All right. So what can be the possibility? We already know that I cannot be 0. All right. So K dot E is equal to 0. And k individually, propagation vector cannot be 0, E individually cannot be 0, all right. So that is why k dot E equals to 0 can only have the idea that E vector, E electric field is perpendicular to the magnetic field k. So E and k are perpendicular, all right. So that means electric field is having vibrations which are perpendicular to the direction of propagation. That means electric field is showing the transverse nature, all right. So this was the transverse nature for the electric field. Again, what we have to do? We have to study the same thing for the magnetic field. How do we do that? We go to all those steps which we have done for the electric field. That means we go to the equation which is having the magnetic field discussion. That means the second equation, divergence of B equals to 0. So we have to go to the second equation for the magnetic field. What we have to do then? We have to do all these things. That means divergence of B is equal to 0 we will have for the magnetic field. So we will write down the this divergence operator, and then we will write down this B in terms of x, y, z here. We will apply the operator. So what we will get? We will get these terms in place of E everywhere. We will be having B. Again, what happens? We have already mentioned that E and B, electric field and the magnetic field, they are having the same nature. That means if E is showing the dependence on x and time like this, so B will also show the dependence of on x and time like this. All right. We can write the same thing for B also. All right. So this whole thing will be applicable for B also. These whole parameters, these whole conditions will be applicable for B also, and similarly we will be obtaining this condition for B also. All right. We must obtain this condition because they are behaving similarly, all right, in the same manner. So when we obtain this condition, the same result we can have for B, that B is perpendicular to the propagation vector k. So now what do we have? Electric field is perpendicular to the propagation vector, magnetic field is perpendicular to the propagation vector, and so we combine both the results, and then we can say that the electric and the magnetic field are vibrations are perpendicular to the propagation vector k. So, the electromagnetic waves are having the transverse nature, all right, because the vibrations are perpendicular to the direction of propagation. So, this is how, with the help of Maxwell's equation, we can verify whether what we have discussed in the very beginning, it is correct or not, all right. So, this is how we can show. So, this is again we can have these vibrations are shown here, all right. The direction of propagation is shown by this arrow, but these arrows are showing the vibrations. You can see that the vibrations of the electric field are shown in this direction, and these are the vibrations of the magnetic field, and that is what is meant by the transverse nature. When the wave is having the vibrations which are perpendicular to the direction of propagation, that is the molecules which are present in the wave, particles which are present in the wave, they are vibrating in a perpendicular direction to the direction of propagation, all right. One more parameter after this discussion, after the transverse nature, after the electromagnetic wave equation, after these things, we can move ahead to other properties of the electromagnetic wave. In the free space, it is very important to mention that what medium we are using, because we can have conducting medium also. The wave can propagate in the conducting medium also. The wave can propagate in the non-conducting medium also. And you have seen in the beginning only that for every medium we have to define parameters. We have to find out what are the parameters which we will be getting for the discussion of the medium, all right. So, when we know something about the propagation, then we can move ahead with other properties like this property, intrinsic impedance or the characteristic impedance. All right. Now, what is characteristic impedance or intrinsic impedance? By definition, if we discuss, so we will see that it is the ratio of the electric field to the magnetic field, and it is defined in this manner. All right. So, it is E by H is equals to mu by epsilon naught square root, all right. In case of free space, we will have mu is equal to mu naught, and these values of the mu naught. In case of free space, we will have epsilon is equals to epsilon naught, and we will have these values. Therefore, if we put these values, so E by H comes out to be 377 ohms or 120 pi. All right. By physical significance, this characteristic impedance means the amount of impedance the medium is going to offer when the wave is propagating in the medium, all right. So, this is one property. These are the references which I have used, and for your course of BTech first year, for this course of electromagnetic field theory, for the propagation of the electromagnetic waves, all right. You can search for the materials in these books. You can also refer to the internet also, all right. And I hope that you have understood about the propagation of the electromagnetic waves in the free space, all right. That was all for this topic. Thank you.